So, today we will look at several non-idealities in capacitance voltage characteristics, but before we do that I just wanted to discuss two important points based on the ideal CV characterization that we discussed in the last lecture. The first one is just to sort of understand how does a CV curve depend on oxide thickness and substrate doping. Okay. We have already looked at various other factors such as measurement frequency dependence, temperature dependence and light dependence during the measurement and so on and so forth. All these are external characteristics, but the device itself can have different oxide thicknesses and different doping concentration. Okay. So, let us just look at the TOX versus TOX and Na dependence. Okay. Of ideal CV, and we are still discussing on ideal CV. Okay. So, let us just consider high frequency capacitance. It would be similar for low frequency as well, and as you recall from our last discussion, if you look at C versus Vg for a p type substrate capacitor, it would look something like this. It has a flat band voltage which is 0. Okay. And the capacitance voltage curve will essentially look like this. Okay. And this is where you reach a strong inversion, and after that you have a flat characteristics. Okay. Let us say this is the case for a particular doping concentration of Na1 and a particular oxide thickness of TOX1. Okay. First, let us consider a situation where TOX1 is kept constant. This is not changed, but this Na1 is varied. Okay. Then let us ask the question, what would happen to the CV characteristics. Again, let us for the time being consider it is an ideal capacitance. Somehow I have made this capacitor so that VFB is 0. Okay. So, the VFB point essentially is out here for all these cases. Okay. Now, if you let us say increase the substrate doping, okay, what you would expect because of that is your threshold voltage should increase, as we have discussed in very early lectures of this course. Threshold voltage has a very strong dependence on substrate doping concentration. If your threshold voltage corresponding to Na1 is out here, your threshold voltage corresponding to let us say Na2, which is higher than Na1, will certainly move to the right, because it will have a higher threshold voltage, right. That is one aspect. In addition to that, the other thing that would happen, as you can well imagine, when you reach inversion, right, the inversion capacitance, eventually the minimum, so called minimum capacitance that we are talking about, you see, depends on what is your maximum depletion width. Okay. And of course, that maximum depletion width will set the minimum semiconductor capacitance that will come in series with the oxide capacitance, and eventually you get the equivalent series combination of these two capacitance. But the deciding factor is really the depletion width, maximum depletion width. As you could now well imagine, as you also increase the substrate doping concentration, due to the fact that the depletion width has an inverse square root relation with substrate doping concentration, the depletion width will decrease, and hence you would expect the capacitance to increase. Okay. So, what it means is that the minimum capacitance should also go up as you start increasing in Na1, right. So, as a result of that, your curve may look something like this. If we say that this is a pivot point here, okay, the maximum capacitance will not change necessarily, because maximum capacitance is essentially governed by the oxide thickness. We are saying that we are keeping oxide thickness constant, we are not changing oxide thickness. Okay. But the Vt will shift, minimum capacitance will also shift. So, your CV curve will probably look something like this. Okay. This is Na is increasing, okay, Na2 now. If you increase Na further, this will increase further, and this will also increase further, the threshold voltage will increase further, right, and eventually you start seeing the curves which would probably look something like this. Okay. Right. So, notice that two things happen with varying Na. Vt increases and minimum capacitance also increases, right, both happen sort of simultaneously. Okay. Now, if you were to consider the other situation wherein you keep Na constant, right, and let us sketch those characteristics as well. Okay. Let us again say that we start with some CV characteristics for certain value of Na1 and Tox1. Okay. Now, I start varying Tox. Okay. Let us say I start increasing Tox. Okay. So, now let us see what happens. If you increase Tox, you would expect, because your Cox has relation epsilon ox epsilon naught over Tox, right, your oxide capacitance will start decreasing as you start increasing the oxide thickness. Okay. And that will certainly have an impact on the maximum capacitance that we will have, because maximum capacitance is solely governed by oxide capacitance, and oxide capacitance starts varying as you vary Tox. Okay. Now, let us ask the question, what will happen to the minimum capacitance? Substrate doping does not change. As a result of that, the maximum depletion width in inversion does not change in silicon, and hence the silicon minimum capacitance does not change. But what we measure externally is silicon minimum capacitance in series with oxide capacitance. Because oxide capacitance is decreasing, although silicon minimum capacitance does not change, the equivalent series capacitance will decrease. Okay, right, because Cox is also changing, right. So, what you would then expect is that if you start increasing the oxide thickness, this obviously will come down. Okay. Let me just illustrate here. Okay. And accordingly out here as well, because although Na is not changing, silicon capacitance is not changing, external oxide capacitance has decreased, and as a result of that your total capacitance will also go down. And when you have started increasing your oxide thickness, your threshold voltage also increases. Okay. So, what you might actually see is a curve which would look something like this, right. It starts moving in this direction and it starts moving down. Okay. And the reason why it happened here is that for threshold condition, again as you remember, just as threshold voltage increases with increasing substrate doping concentration, threshold voltage also increases with increasing oxide thickness. Okay. So, this threshold minimum capacitance point shifted to the right, and also the minimum capacitance value came down. On the other hand, let us say this is for Tox 2 which is greater than Tox 1. Now, if I choose another Tox which is less than this, okay, then your capacitance here will increase, because now I have chosen Tox 3 which is less than Tox 1. You see, this will increase, and because oxide thickness decreased, your Vt will also decrease now. Okay. And hence it will probably look much more steeper, and your minimum capacitance will increase now, because your oxide capacitance which is coming outside in series with the silicon capacitance has gone up now. Okay. So, your CV may look something like this. It will have a saturation at lower value of Vg, because your Vt has come down. Okay. At the same time your minimum capacitance increase, because your oxide capacitance increase, right. So, your total capacitance sort of goes up and down, okay, because your oxide capacitance is changing. As a result of that, the capacitance in the entire CV range will go up and down, as opposed to this case where only substrate doping was changing. Okay. So, these are some very important differences that you may want to keep in mind. In fact, in the next lecture we will also discuss, once you do a CV measurement, how can you start extracting various parameters, but this is something that will be useful to remember when we have that discussion. Okay. Now, one other point that I wanted to discuss is CV on, we have been talking about MOS capacitors, but we also build transistors using these, right. So, is there any difference in CV of a capacitor device and a transistor device? In other words, the question that I am asking here is that you have p type substrate, let us say you have oxide, and you have essentially built an electrode here which is your gate. Now, this is essentially a 2 terminal capacitance device, and you have another device wherein everything looks same. You have this similar gate area and all that, but in addition you have also made junctions here, n plus, okay, and there are contacts to the junctions as well, and let us say we have connected all these together, whereas here this is the low point and this is Vg. Okay. So, both have the same area, so you would expect the capacitances should be similar, because the capacitance is essentially governed by what is happening here. Okay. However, there is one very important difference that you have to keep in mind, and that is their behavior under high frequency characteristics. Okay. Let us say this is C. The low frequency capacitance, if you do LFCV measurement on this structure as well as this structure, you get a curve which will be exactly identical, right. Let us say if this is the curve for capacitors, then your transistor curve will essentially overlap on top of each other. This is what you expect, because anyway the area is same, so your capacitor that is formed is identical really. But your high frequency capacitance in a case of this device, as you know, will essentially look like this, right. In inversion you have the minimum capacitance under high frequency. This is your HFCV for capacitor structure. On the other hand, if you were to do this on a transistor, you see the transistor will give a capacitance voltage characteristic which will look exactly like a low frequency CV. In other words, if you are doing the CV measurement on a transistor structure with the connections as shown here, whether you do the CV at high frequency, low frequency, it does not matter. They always are identical, exactly identical, and all look like a low frequency CV. Only in a capacitor structure in inversion your capacitance is quite different from the low frequency capacitance. And if you think about this, this is obvious and it is no surprise at all, because as we discussed in the last class, the very fact why we got a capacitance which is lower is because the electrons were not responding in a capacitance structure. But you see, now you have given a huge reservoir of electrons here, right. This is n plus. Okay. There are a lot of electrons which are available right next to that capacitor. So, you do not have to generate these electrons in a depletion region. So, these electrons will come back and forth instantaneously in this structure, because of the fact that just as the majority carrier holes are available in this capacitance, and hence you do not see any difference in accumulation region. Now, in inversion region also, although you do not have electrons as majority carriers here, but there are 2 junctions which are sitting right next to it, which have electrons as majority carriers. Okay. So, you do not need to generate electrons anywhere else in this device. These electrons can come back and forth instantaneously, and hence there is no dearth of availability of electrons. Electrons respond instantaneously, and hence your semiconductor capacitance is very large. It is no longer the depletion capacitance, because you do not need the depletion edge to respond. The inversion charge right here is responding instantaneously, as opposed to the depletion edge responding, you see, and hence you do not see any difference here. Okay. This is another important point that you need to that is why we make these junctions, right. So, that instantaneously we can turn on and turn off this transistor. Otherwise, you would not turn on the transistor at terahertz frequency if you have to wait for these electrons to generate, because of the generation that is happening, right. Because we have this source, so called source junction, but here both are source junctions because both are at ground potential. But in the transistor action, one of them is at positive potential, that cannot source because you are draining the electrons there, but the source can instantaneously supply electrons into it, right, and that is how we can switch the transistor at very high frequency. Okay. Okay. So, now let us look at okay. The first thing that we will look at is non-zero flat band voltage. So, VFB not equal to 0. What are the contributors for VFB? Essentially, as you may recall, VFB is the work function difference between the metal and silicon, right, because in ideal capacitance we said I have chosen a fictitious metal which has the same work function as silicon, but that will never be the case. Okay. Your capacitors made on p type silicon are likely to be for n channel transistor, and they will have their work function on the gate side which is closer to the conduction band of the silicon. It will be like n plus on the gate, okay, and hence there is a phi ms. And in addition to that, you can also have what is called fixed oxide charge. QF here refers to fixed oxide charge, meaning oxide is also not perfectly ideal. Ideal oxide will not have any charge inside it, but a non-ideal oxide can have some non-zero charge inside it, and that would also impact your capacitance voltage curve. Okay. So, now let us look at the impact. So, let us say this is my ideal CV curve, okay, which has VFB is equal to 0. One important thing that you want to recognize here, the capacitance value at any gate voltage is uniquely determined by the surface potential in silicon. In other words, when you have the accumulation condition, if you recall, if I am looking at a p type substrate, and if this is my oxide interface and this is my p type substrate, what will happen? I have an accumulation region which is this. If this is EF, bands are bent up like this, you see, correct. That is, I have more holes here, and that is what is called accumulation region. And at this condition I have flat band. What is flat band? You know, if this is my oxide interface again, my bands are perfectly flat, that is psi s is equal to 0. And as I am going in this direction, now I start seeing some depletion, okay, this bands will start bending like this, okay, right. Again you see surface potential has changed, surface potential 0, surface potential negative, surface potential positive, going down is what we treat as positive surface potential, okay. And eventually when you reach inversion, these bands have bent so much that your band bending is 2 phi b and you have reached inversion condition. In other words, the capacitance value is uniquely determined by psi s, right. There is a very specific one to one correspondence between the silicon capacitance and the psi s, the band bending, the value of psi s. As long as you have the same psi s, you will get same capacitance, that is the message, okay, because you see it is only the silicon capacitance that is variable, oxide capacitance is not variable, okay. So, in other words, now when I have a non-zero VFB, all that it would do is that in order to get a flat band condition under which I should get this capacitance, by the way this capacitance is called CFB. Once you fix your device oxide thickness and doping concentration, CFB will never change, okay. So, if you have a different phi ms, non-zero phi ms, it will give non-zero VFB, okay, and similarly if you have a fixed charge, it will give non-zero VFB. All it will do is that it will translate the CV curve along the gate voltage axis. In other words, if my VFB let us say is minus 0.5 volt, what it means is that in order to get CFB value, I need to go to minus 0.5 volt, okay. This is where I will get this capacitance value, and after that as I start applying more gate voltage, it will go towards this, and hence capacitance will start increasing, and I start applying positive voltages beyond minus 0.5, bands will start bending like this, capacitance will start decreasing like this. So, in other words, what you will have is really this, Okay. So, there is this translation, okay, important point. So, VFB due to phi ms and QF translates CV curve, translates the ideal CV curve, that is whatever you got based on your ideal CV characteristic, it just translates either to the left or to the right depending on whether your VFB is negative or VFB is positive. Okay. In fact, as we will see in the next class, in fact this is the information that we use to find out what is the fixed charge in the oxide when you actually measure a device. Okay. Because once you measure a device, I can generate a ideal CV, we will talk about it in the next class, and then I can compare an ideal CV with the experimentally measured CV, and looking at the difference I can generate all these non idealities in a capacitance voltage, I mean the MOS capacitor. Okay. Now this fixed, by the way, phi ms is very obvious, you have different work function. This fixed oxide charge is essentially attributed in case of silicon oxide, at least QF is always positive, and essentially what is attributed is that if you have this silicon oxide, you have to grow this silicon oxide on top of silicon. Okay. When you are growing this silicon oxide, you are transitioning from silicon to maybe silicon oxide as I start growing thicker and thicker oxide, but in this transition region, this transition region is really non-ideal. In other words, you really have something like SiOx. You see, when x equal to 0 you have silicon, when x is equal to 2 you have SiO2. Okay. But here you have really SiOx, it is not perfect silicon, not perfect silicon oxide, something in between, right. So, this is really a non ideal thing. So, what is proposed really is that you really have in this was supposed to be silicon oxide with an abrupt transition, but really in this region you have oxygen vacancies. That is why your oxygen is no longer 2, it is less than 2, where your x is less than 2. X is less than 2 because you have oxygen vacancies. Okay. What I mean by that is that if you were to look at the silicon oxide matrix, the silicon oxide matrix will essentially look like this ideally. Okay. You see, silicon has valence of 4 and all that is satisfied, oxygen has valence of 2 and that is also satisfied. But let us suppose that this oxygen is not there, this is missing, then this is what is called a defect site, and this defect site ideally should have one electron from silicon and one electron from this silicon, but it tends to lose one of the electron, right, because it can't hold that electron there, and hence this defect size becomes positively charged. Okay. So, that is a very plausible, very simple model that is given, and in fact this has also been validated by doing lot of structural characterization of silicon oxide, right. So, invariably whenever you grow silicon oxide on silicon, you have this transition region, and this transition region has lot of oxygen deficiency, okay, and that oxygen deficiency results in a missing oxygen atom and a defect site which becomes positively charged, right. So, invariably whenever you are doing MOS capacitance characterization on a SiO2, you will invariably see that because there is a positive charge, the CV will always tend to shift left. Okay. This is obvious, right. If you have positive charge, your inversion voltage also decreases, right, and that is also obvious, right. You have positive charge, this positive charge can attract electrons, right. In other words, you need to reach inversion much earlier, correct. So, if you have a negative charge, it will be the opposite, it will shift to the right. Okay. So, QF is something very important that you need to consider, right. So, this is essentially one of the non ideality. The next non ideality which is also very important, is what is called interface traps. It is denoted as QIT, which stands for interface trapped charge, or DIT or NIT. There are different ways of so QIT essentially means interface charge. In other words, I am essentially saying coulomb per centimeter square, so much charge is available. NIT means defects or traps density. Okay. This is charge density. Okay. That is why it is per centimeter square. Here it is number per centimeter square. Okay. So many 10 power 12 traps per centimeter square. So, there is no charge here, you multiply NIT with Q, you get QIT. Okay. So, that is QIT is Q times NIT, you are converting it into charge. Okay. And DIT is something is again a density, but its density, trap density, not just defined in terms of areal density, its density in terms of area as well as per unit energy. It becomes clear in a minute what we mean by that. In other words, the unit of this is per centimeter square EV. Okay. And this EV is essentially what I meant. It really tells you per unit value of energy in the band gap what is the density. Okay. So, first of all, what are these interface traps? As the name suggests, when you have silicon and oxide exactly at this interface, the fixed oxide charge is little away from the interface. Okay. Whereas, interface state charge that we are talking about is exactly at this location, and hence the name interface charge. Okay. Going from silicon into silicon oxide exactly at this interface. Okay. Now, again if you see at this interface, you have lot of non-idealities, right. You have some silicon atoms which is sitting here, right. The silicon was happily sitting here bonding with 4 neighboring atoms, but here you do not have a silicon here, right. So, here you have what is called a silicon dangling bond right at the interface. Okay. And similarly, you may have an oxygen here, okay, and that oxygen bond length with silicon may not be perfect as it should have been in silicon oxide. Okay. So, all these are defects again, and these defects are exactly at interface. And this is very important, and hence because they are exactly at interface, their charge state changes. That is the major distinction between the fixed charge that we discussed. Fixed charge is little bit away from the interface, right, not exactly at the interface, right. This region which is a transition region, this is where the fixed charge is, and this being away from the interface, it does not interact with the silicon underneath, and its charge state does not change, and hence the name fixed charge. Whereas, the interface charge, its charge state changes, it can either get an electron or release an electron, it can be positive charge, neutral or negative charge depending on the nature of the defect. Okay. Now, these defects is what is going to impact your CV characteristics and hence the behavior of the MOS capacitor and transistor very significantly. Okay. Now, this is in terms of position. Let us look in terms of energetics. Now, this is my silicon, let us just consider flat band condition, and this is my oxide, right, which has huge band gap as we have been discussing. Okay, and you have some gate metal, it could be anything, some let us say N plus polysilicon. Now this is silicon and this is SiO2 and this is gate. Silicon here is perfect band gap Eg, there are no allowed energy states here. Okay. Oxide again no allowed energy state in between, large band gap. But this transition region is non-ideal and it has large number of allowed energy states. This is an energy picture of the same phenomenon. In terms of the physical defect, the physical defects are exactly at the interface. Those physical defects in turn translate energetically either traps closer to the valence band, traps closer to the conduction band and traps somewhere anywhere in the middle of the band gap. And experimentally, it has been seen that if you were to really go from valence band edge to the conduction band edge in terms of energy, okay, in terms of your trap density, you get a distribution which looks something like this. At the middle of the energy, which is what is important as far as transistor capacitor operation is concerned. This is a region when we are applying gate bias, this is a region wherein we are moving the Fermi level. We are moving the Fermi level from accumulation towards the inversion region. Okay. We do not go very close to valence band anyway, we do not go to very close to conduction band anyway. And now this here distribution is what is called DIT, okay, because this is given as a function of energy value and per unit area value. Per unit area at a given energy, what is the trap density? That is what we call DIT, interface trap density in terms of number per centimeter square EV. So from DIT, if you want to get NIT, you integrate this over a energy range, right. In other words, you get NIT as integral from E1 to E2, right. DIT, which is of course a function of E, dE will give you NIT. Now you see, you can sort of make correspondence with all these, right. So DIT has a unit of per centimeter square EV, because you are integrating over dE, EV gets cancelled in terms of dimensional consistency and you get the trap density, which is number per centimeter square. Okay. So this is what I meant DIT, this is density which is not only areal density but also energetics. Okay. Now what is the impact on the CV, right? What happens when you are doing CV, right? When I have flat band condition, if it is a p type semiconductor, as you know, the flat band condition, the Fermi level looks like this, bands are perfectly flat. And in fact, if it is inversion accumulation condition, then these bands will actually bend like this, correct. I am just keeping Fermi level as constant, I am not disturbing that, I am just changing the bands to sort of see what is happening. Okay. Now you see, when you have the Fermi level here, again based on the Fermi Dirac statistics, you can say that everything above the Fermi level is empty, there are no carriers there, no electrons there, everything below the Fermi level is filled with electrons, right. That is how we define Fermi level in the easiest manifestation of the Fermi level definition. What happens under inversion? If I go into inversion, the bands, as you know, will bend downwards, you see, correct. As you know, the Fermi level comes closer to the conduction band, that is why it is N like now, because it is inverted now, and here in accumulation Fermi level was very close to valence band, it was very heavily p like, right. So now the bands here, the traps that we are looking at, these are the interface traps, you see. Now what happens when I sweep the gate voltage from accumulation to inversion? The location of the Fermi level with respect to band edges is changing at the surface, or the bands are bending with respect to Fermi level, one and the same. So in other words, what has happened here, you see, in accumulation most of the traps were empty and inversion most of the traps are filled. So, when I am sweeping the gate voltage from one extreme to the other extreme, the charge state is changing, and hence it is not fixed charge, it is a variable charge. The variable charge, the exact quantity depends on the exact value of gate voltage, because exact value of gate voltage in turn dictates what is your band bending, and that in turn dictates how many traps are empty, how many traps are filled. Okay. Right. So, now the conclusion based on this discussion is that the QIT is not fixed. Okay. In other words, changes with respect to psi s. Psi s is changing, as a result of that you will also have this variation. Now, the next question to ask is that, okay, now we have understood at least the charge should be changing. Now, is it going to be positive charge, negative charge? Now, how is the charge going to change? Okay. Now, that depends on the nature of the interface traps, okay, and based on all the experimental studies again and lot of theoretical studies as well, a fairly good model for interface state traps has been evolved, and that essentially states that if you have traps in silicon distributed from the conduction band all the way to valence band edge, right, the model says that the traps above mid gap behave as acceptor like traps. We will see what it means by that. And the traps below mid gap right behave as donor like traps. Okay. Now, the donor and acceptor like essentially sort of used here, the actual donor, if you are talking of phosphorus as a donor, donor is very close to conduction band, correct, it donates an electron. So, obviously, the traps are not good donors right, because they behave as donor like, but they are below the mid gap, they can't really donate. If there are any electrons, they can catch the electrons, but they can't really give out electrons, you see. Similarly, acceptor, an ideal acceptor boron, its energy level should be very close to valence band, only then it acts as a very good acceptor, it donates holes. But here these so called acceptor like traps are above mid gap, so they are certainly not going to donate you any holes. Okay. So, these traps are not going to give you any extra free carriers, but they actually instead take out the free carriers. Now, when they trap these carriers, the question is whether they will have positive charge and neutral or neutral and negative charge, okay, because you can only change between two states, right. You can go from neutral to positive or you can go from neutral to negative, you can't go from negative to positive unless it captures multiple carriers, okay, that does not happen. In other words, let us consider arsenic atom. Arsenic atom can either be neutral or when it donates an electron it becomes positive, but it can't become negative, okay, right, because when it has all the electrons filled it does not have any tendency to get an extra electron over there, you see. So, arsenic atom in silicon can either be positively charged or neutral. Similarly, a boron atom in silicon can either be neutral or negatively charged, correct, but it cannot be positively charged. So, the meaning of this is only that if it is a acceptor like trap, it can either be neutral or it can be negatively charged. Okay. If it is donor like, it can be either neutral or positively charged. So, that is how these states behave. Okay. More particularly, if you have an acceptor like state, if it is filled with electron, okay, then that will have a negative charge. Okay. On the other hand, if you have a donor like state, if it is filled with electron it will be neutral. Okay. A donor like state which is empty of electron will be positively charged. Okay. So, and again acceptor like state which is filled with electron will be neutral. Okay. So, in other words what you essentially have, if we again look at this band picture, I mentioned, let us consider this is EI, okay, then this is EC, EV, and we just said that all these above mid gap, this is mid gap, above mid gap are acceptor like, and all these below mid gap are donor like. In other words, when my Fermi level is exactly at mid gap, if Fermi level is exactly at mid gap, what does it mean? All these donor like states are filled with electron, they have not donated electron, these traps, and hence they will all be neutral. Okay. And all these acceptor like impurities are empty of electrons, they are not filled with electrons. If acceptor like states are empty of electrons, again they are neutral. In other words, when you have the mid gap condition, when the surface potential in silicon corresponds to the mid gap condition, then interface traps do not correspond, do not give any extra charge. So, that one point which will act as a pivot point will be exactly same with QIT is equal to 0, or meaning DIT is equal to 0 or DIT non-zero, that will be the same point. Okay. When this starts coming down, you see, when this starts coming down, these acceptor states continue to be neutral because they are anyway empty, they continue to be empty, but some of these donor states are now getting uncovered, they will leave out an electron. Now, lot of donor, more particularly when this comes all the way down, that is what happens in an accumulation condition. In an accumulation condition, bands are bending at the surface, Fermi level is very close to valence band, meaning most of the traps are empty. Okay. So, anyway acceptor traps which were anyway empty are not going to give charge, but all these donor like charges will now give positive charge. Okay. So, more particularly now when you have accumulation condition, this is your accumulation condition, correct. This is Fermi level, this is EV, this is EC, you see all these traps are empty, most of the traps are empty, and these acceptors do not give any charge, but you have net positive charge here. Opposite thing happens in inversion. In inversion, the bands will start bending down, the donor like traps are all filled now in invert. Anyway, whenever they are filled, they do not give you any charge, but acceptor like traps, as soon as they start getting filled, they start giving you a negative charge. Okay. So, in other words, if you see here, this is how you will have your okay, correct. So, now most of the traps are filled because now the EC has come very close to Fermi level. So, most of the traps below Fermi level are all filled. Donor like traps are not going to give anything extra to me, mid gap is somewhere here, okay. But these traps which are acceptor like traps, you see, they are all filled with electron, they give negative charge. Okay. So, when I am going towards inversion, I get, so as I go closer and closer to the inversion, I am feeling more and more negative charge, and the charge magnitude is increasing towards more and more negative. At mid gap 0, as I start going towards accumulation, the charge magnitude will again start becoming more and more negative, as we discussed here, because more and more donor states are getting uncovered. So, this is what is going to result in a phenomenon called stretch out of a CV curve. Okay. What it means is the following, right. So, now again let us look at the capacitance voltage curve. Let us say this is my ideal CV with VFB is 0. If VFB is non-zero, this will probably have a parallel shift, Now, in case of interface states, right, what will happen? Okay. So, somewhere here this is VFB, this is all flat band, right. Somewhere here I have a mid gap condition, you see, this is flat band, this is deep accumulation, this is deep inversion, and somewhere here I have a mid gap condition. At mid gap condition there are no extra charges because of interface states. Okay. So, which means your capacitance value will be exactly here for this gate voltage. But now as I start going towards this direction, I start getting more and more positive charge. Positive charge will tend to shift the capacitance to the left, remember, but it is not fixed positive charge. The positive charge starts increasing as I start going away and away. So, in other words, this curve starts looking like this. You see this shift, that shift is due to positive charge, and because the positive charge is increasing, this shift is also increasing, it is not a parallel shift, you see. Similarly, in this direction I start having negative charge. Negative charge will tend to shift the CV to the right, okay, and again more and more negative charge starts coming up, and hence the CV comes up like this. So, in other words, you see this is what we call stretch out. CV, it is as if you have taken that CV and you have stretched it out, you see. So, that it takes much larger voltage span to go from accumulation to inversion condition as compared to a much shorter voltage span to go from accumulation to inversion. So, now if you have higher and higher trap density, that is interface trap density, your stretch out will be more and more. Okay. If let us say this is for DIT1 and now you have DIT2 which is even higher than this, then the stretch out is even much more. You will probably get a stretch out which will look like this. This could be DIT2 which is much greater than DIT1. Again at this point you may not have any charge, okay. As I start going to the left, more and more positive charge continues to increase, and in this direction more and more negative charge continues to increase as it increases, right. This is essentially the stretch out phenomenon. This is as far as high frequency capacitance is concerned. Okay. Now, there is something interesting, and that is this interface states is traps or states, we use it interchangeably, also impacts CLF, low frequency capacitance. Now, that is a little bit interesting thing to look at. If I have this C versus Vg, okay, let us say that I actually do the measurement instead of being very sharp ideal CV, okay, high frequency CV, let us say this is high frequency, and accordingly the low frequency will probably like this, correct. And now because of the interface state density, let us say that the CV curve actually looks something like this. Okay. Now, based on this discussion, I mean we have not discussed what else will happen to low frequency CV. The minimum that you would expect is that because high frequency looks like this, the low frequency at least should come up like this and go up here. Even the low frequency should be stretched out, just as high frequency gets stretched out. But very interestingly, that is not the only effect for low frequency. There is another effect for low frequency curve, and that is in the region between flat band to inversion, that is in the depletion region, your low frequency capacitance, your low frequency capacitance will be little higher than the high frequency capacitance, and of course eventually it will go up like this, and indeed low frequency is also stretched out just as high frequency is also stretched out. But earlier, in the presence in the presence of ideal condition, meaning no DIT, the low and high frequency not only superimposed on each other at accumulation, but also throughout depletion, and then they started departing. But here, even in depletion, the low frequency capacitance is higher than high frequency capacitance, and this is essentially because the low frequency capacitance value is also increased because of trap capacitance. In fact, we model this as CIT, which stands for interface trap capacitance. Okay. In other words, more specifically, remember the equivalent model that we had. I had Cox, I had C silicon here, correct. This is my equivalent, and now I have something called CIT. Now, what is the CIT? Just as CS is defined as, how do you define that CS? Minus dQs by d psi s, correct. Whenever I try to change the surface potential, there is a corresponding change in semiconductor charge that constitutes a semiconductor capacitance. Precisely on the same definition, as I am trying to change the surface potential, traps are also changing their charge states. There is certain charge in the traps which we call QIT, and this QIT is changing, correct, is precisely what we discussed. I am trying to change the surface potential, and that changes the charge in the traps, and hence we define this term called CIT, which is minus dQIT by d psi s. That is, when I go from one surface potential, certain band bending in silicon, to a second surface potential, that is d psi s, I not only will generate some charge in silicon, but I will also change the charge in traps, correct. So, there is a change in voltage and there is a corresponding change in charge, and that is capacitance for you, right, and that is now a trap capacitance or CIT, okay. And this is the total charge that when I put a gate charge, accordingly this is the total charge that is responding in silicon, partly at the interface and partly in the rest of the silicon, and that is why we say that these two are in parallel, okay. Now, as you would imagine, if this is the case, then your semiconductor capacitance would be increasing. You see, if I try to measure the capacitance Cox in series with Cs in parallel with something else, you would expect the capacitance to change because of CIT, and that is precisely what happens in this region for low frequency, but not at high frequency, very interestingly. Why is that? Again, exactly what we discussed. At high frequency, I am changing the signal very fast, and hence these charges which are trapped in these defects, they need some time to empty or fill. I am not giving enough time for these to empty and fill, okay, because my measurement frequency is so fast, and hence when I am doing high frequency measurement, I do not get that extra capacitance. When I am doing low frequency measurement, my frequency is so low that I am giving enough time to fill these traps, empty these traps. As a result of that, the CIT will come in only at low frequency, okay, and hence this is what you see, okay. So, CIT at LF, but not at HF, right, makes sense, right, and hence at any given point here, at this point you do not see that difference anyway, because all your capacitance is dictated by Cox, okay. And again here this is as expected, this is dictated by the maximum depletion width, minimum capacitance, and again this is governed by whatever you have in terms of the oxide capacitance. but here where they were supposed to be exactly identical on top of each other, you see this difference, and this difference, you know, whatever you have in this depletion region is due to CIT, okay. And that is what you see. So, this is a very interesting impact on low frequency in addition to the stretch out, okay. Now, why did the stretch out happen? Again, you must understand this. When I went from this gate bias to this gate bias, remember exactly what the discussion we had in high frequency. I am giving enough time, for that to settle down. So, when I go from this point to this point, I have given enough time to fill and empty these traps. That is why there is a stretch out, because in order to generate that many charges in silicon to get that band bending, first I need to take care of the trap charges, okay. So, that is why the CV is getting stretched out. I need to put in more charge on the gate, because there is more charge that needs to be generated in silicon, not only for that you know, the usual depletion charge, but also the trap charge. And because I am doing slow step, the stretch out is responding to the slow variation, slow ramp that I have, but at any gate voltage my measurement frequency is too fast or too slow. So, for that measurement frequency, only when it is low frequency I have higher capacitance. At high frequency I do not see that capacitance, you know, due to interface traps, because frequency is too fast, okay. So, let us just recap then what we discussed. We looked at the ideal CV, re-looked at it and studied the impact on impact of oxide thickness and doping concentration, and recognized the fact that transistor structure, if you do capacitance voltage measurement, no matter whether you do a measurement at high or low frequency, you always get a curve which looks like a low frequency curve, because of the fact that you have this reservoir of electrons, okay. And then subsequently we started looking at the non-idealities, and the VFB, non-zero VFB comes because of work function difference or the fixed oxide charge. If the fixed oxide charge is positive, the CV will always shift to the left. If the fixed oxide charge is negative, not in silicon oxide, but in some dielectrics it could be, then the CV could shift to the right, okay. But this is always a parallel translation, no stretch out compared to ideal capacitance voltage characteristics. On the other hand, when we talk of interface states, these are exactly at the silicon oxide transition, and hence they communicate with the channel charge, depending on holes, electrons, whatever is there, you know, they can easily go back and forth, and hence you have a varying charge, and the DIT is defined as a function of what is the density in the band gap, and because this is distributed in the band gap, the charge state varies depending on the location of the Fermi level, okay. And given that, if we go with this model that above mid gap is acceptor and below mid gap is donor like, you know, then the CV will essentially stretch out with the pivot point being out here, right. CV will always stretch out in place of interface traps, okay. Where is the pivot point depends on where is the charge neutral condition. Here we have said charge neutral condition is at mid gap. And then finally, low frequency capacitance also gets impacted because of DIT, and that is simply because there is also a trap capacitance. In fact, CIT is given as QDIT. This is how we define. This definition will translate to this definition, okay. They are equivalent definitions. Okay. We will stop here, and in the next class we will continue discussion on other non-idealities and the actual measurement and extraction of parameters.